Okay, so there's I think two more examples for L'Hopital's rule, and these again are not our direct indeterminate forms where L'Hopital's rule can be used. As a recap, just remember to use L'Hopital's rule, you have to have a comparison of two rates. So like your rates either you directly can put the limit and you get a 0 over 0 or infinity over infinity. Those are the two indeterminate forms that you can then apply L'Hopital's rule to. Now, if I let x go to infinity here, 5 infinities times or plus 1 is still infinity, and then 1 over infinity is like infinity to the 0 power. Okay, so this is not one of our forms where we can apply L'Hopital's rule. So the way we're going to try to transform this is let's look at for a second. Let's look at what 1 plus 5x raised to the 1 over x power. Let's call that y. And what we're going to do is we're going to take the log of both sides. So then I'm going to bring the 1 over x down times the natural log of 1 plus 5x. And then that 1 over x that we brought down, right, as the exponent came down in front as the coefficient. So then we get natural log of 1 plus 5x over x. So let's think about that for just a second. What if we do the limit as x goes to infinity to that quantity? And just remember that that's equal to the natural log of y of our function. So keeping track of, kind of keep track of that in the back of our head here. But let's look at what happens as we take the limit as x goes to infinity of the natural log of 1 plus 5x over x. So as x goes to infinity, we do get the natural log of infinity, which is still infinity. I mean, the natural log slows it down a bit over infinity. So we do have one of our indeterminate forms where we can use L'Hopital's rule. So I'm going to say, okay, that equals by L'Hopital's rule. Now it's the limit as x goes to infinity. Well, the derivative of the top is 1 over 1 plus 5x times chain rule, 5, divided by 1. And so let's see what that really looks like. So that is still equal to the limit as x goes to infinity of 5 over 1 plus 5x. So then as x goes to infinity, 5 times infinity is right infinity plus 1, so still infinity. So basically this whole fraction goes to 0, right? Goes to 0. So then I think, okay, well, all right, it goes to 0, but remember that's what the natural log of y was equal to. Natural log of y was equal to 0. So if I e to the both sides, right, to undo that, that means that our y value is equal to e to the 0 power, and e to the 0 power, which is equal to 1. So that means our limit as x goes to infinity of this function right here, which we said was infinity to the 0, actually equals 1, which is kind of interesting. Something that infinity to the 0 power in that case equaled 1. And you might say, well, that's easy because anything to the 0 power is always 1, and not necessarily true. But that's how you can deal with an exponent that has one of your variables. Okay, we're going to see that again in example number 7. Right? Now we're going to let x go to 0. Good. We have another example here. So now we're going to go to 0. Who else gets excited about more math? Right? As x goes to 0, so we get 1 raised to the, and then when you put 0 here, you get an undefined term. So 1 to the infinite power. And again, this is one of my favorite ones because you think, again, like 1 to the infinity. 1 times 1 times 1 times 1 forever. Like you just keep on multiplying by 1. Shouldn't that equal 1? And spoiler alert, no, right? It's not, and we're going to see why. So this is really cool. So same concept. Let's call this y. So let's let y equal the quantity 1 minus 4x to the 1 over 3x 1 over 3x. Okay, now let's natural log both sides. And when we do that, the 1 over 3x comes down. So it's natural log of 1 minus 4x. And we can construct that. So it's the natural log of 1 minus 4x over 3x. And if you think about doing the limit as x goes to infinity of that expression, well knowing that it's really the natural log of y, and we can e to the both sides to fix it. So the limit as x goes to 0 of that expression, well, we get natural log of 1, which is 0, and 3 times 0 is 0, so we get 0 over 0. So we have that characteristic structure format of an indefinite or indeterminate form of a number, and I can apply L'Hopital's rule. So that means I'm going to say it equals, by L'Hopital's rule, the limit as x approaches infinity of the top function's derivative. So that's 1 over 1 minus 4x times negative 4. There's your chain rule, divided by the derivative of 3x, which is 3. And so now I can look, and that's a negative 4 over 1 minus 4x when divided by 3. And we can certainly move that 3 up here. So we get negative 4 over 3 times 1 minus 4x. Okay, so remember, we're taking the limit as x approaches 0. So the limit as x approaches 0 of what we just came up with, negative 4 over 3 times 1 minus 4x. So as x goes to 0, we get negative 4/3. And then remember, that's the natural log of y, right? Because we had logged both sides. So if the natural log of y then is equal to negative 4/3, then y would have equaled e to the negative 4/3, right? Which is crazy, right? I mean, think about that. That's 1 to the infinity in this context equals e to the negative 4/3, right? Not 1, right? So crazy, and yet cool at the same time. So I think. All right. So then let's do one more example. I forgot we had this little guy down here, example 8. Now, when you let x equal 1. Natural log of 1 is 0, so you get 1 over 0, which is undefined, or as you approach it, you get a very large number. And as you approach 1 from here, you also get a very large number. So we get this idea of infinity minus infinity. Well, infinity minus infinity doesn't have to be 0. It depends on the density or the rates of these infinities. So, but when you have something like this, perhaps the easiest thing to do is to find a common denominator. So let's go ahead and do that and switch colors here, kind of change things up. So we're going to get x minus 1 minus the natural log of x over natural log of x times x minus 1. Right? So I'm just finding that common denominator, and then we'll let the limit as x approach 1. So when you let x equal 1, 1 minus 1 is 0 minus natural log of 1, which is still 0. And then natural log of 1 is 0, 1 minus 1 is 0. So now we have 0 over 0. So now I can, in fact, apply L'Hopital's rule. I might want to multiply that bottom out just maybe to make it a little bit easier. So x minus 1 minus natural log of x, and then divided by x natural log of x minus natural log of x. So I haven't really done anything yet other than just distribute in the denominator. Okay, now let's use L'Hopital's rule so we can take the derivative and compare the rates. So limit as x approaches 1. Well, in the numerator, the derivative is 1 minus 0 minus 1 over x. And in the denominator, we have a product rule. So the derivative of x is 1. Leave ln x alone. Then leave x alone. The derivative of ln x is 1 over x. And then the derivative of ln x again is minus 1 over x. So when we now put in, so I guess I can clean the denominator up just a little bit, not a whole lot. So 1 minus 1 over x in the top. And in the bottom, is natural log of x plus 1 minus 1 over x. So let's let x go to 1 this time. As x goes to 1, we get 1 minus 1 over 1, so 1 minus 1, which is 0, and natural log of 1 is 0, and then you get a 1, and then minus another 1, so we get 0. Oh, this is great. We can use L'Hopital's rule again, right? How exciting. So I'm not really sure where this is going to go, but we'll find out together. So the limit as x approaches 1, so the derivative of the numerator, 1 goes away, and remember, negative 1 over x, that's the same thing as negative x to the negative 1. So then its derivative would be positive x to the negative 2, or like 1 over x squared. So that's the derivative of the top. Derivative of the bottom, natural log of x is 1 over x. 1 goes away, and then we have that exact same derivative, so plus 1 over x squared. Okay, now let's let x go to 1. So as x approaches 1, we get 1 over 1, which is 1. And then we get 1 plus 1, which is 2. So we get 1/2. Wow. So think about what we just found. In this case, infinity minus infinity. Originally, right, we have these infinite large numbers. The value is 1/2. This limit value is equal to 1/2. So again, to me, it's such an interesting concept, right? It really gets at the heart of that infinity is not a number, right? Because if these were numbers, these would be identical and it would be 0. So infinity is this concept and of direction, right? And like how fast do you get to that infinite number or the infinite direction varies. And so when you start comparing that as you go out over time, you can actually evaluate and say, okay, well, you actually get 1/2. So that means that somehow the first infinity is slightly bigger than the second infinity for that to equal a value of 1/2. And when I say slightly bigger, has to do with its rate. So anyway, what a cool problem. So hopefully those two examples, or I should say 3 examples, a little bit more challenging, and that'll give you enough with the first video to answer the homework questions.